Okay. So my talk is based on joint work with Gabe Frieden, who is currently at Macdonald University. And our aim is to give a tableau theoretic proof of the dual Cauchy identity for Macdonald polynomials, which is shown here. And I will start by introducing all these basic notions we need, meaning like I will talk about the classical Schur case. And whenever there is a star here, this means like dual. So I'm not talking about RSK, I'm talking about dual RSK due to time limits. Then I will talk about like how the situation changes when we go to the Macdonald polynomial level. And finally, I will talk about or basically more sketch our correspondence and talk a bit about its properties. Okay, so for me, a partition is a weakly decreasing sequence of positive integers, and I usually depict them by using Young diagrams. And since this work started while both of us have been in Montreal, I'm sticking to French convention for this talk. And we have the conjugate, which is just denoted by lambda prime. And also we need skew diagrams, which I assume like most people know anyhow. Okay. And then we also have seen standard Young diagram, a standard Young tableau in a few talks already. So these are fillings of Young diagrams of integers, positive integers, such that rows are weakly increasing and columns are strictly increasing. So here you see an example of a semi-standard Young tableau of shape 4, 3, 1. And for each semi-standard Young tableau, we define a weight denoted by bold x to the t, which is just the product over xi to the number of i's appearing in T. So in this example, we have 1, 1, so meaning we have 1x1. We have 3 2's, so x2 cubed, and so on. And with this, we have all the ingredients to be able to define Schur polynomials in a combinatorial way, because they're just the generating function with respect to this weight. So, oops. So here, Schur polynomials are defined this way. And since I'm talking about polynomials, meaning we're restricting the number of variables to n variables, if you want to do Schur functions, then you have an infinite amount of variables here. But in our case, we're restricting, because of this, the entries of the tableau to be from 1 to n. And it's very useful for this talk, and I feel like in general, to use this combinatorial description for Schur polynomials, but rewrite it slightly in a bit more algebraic way. And for this, I need up and down operators. But first, a horizontal and a vertical strip. So a horizontal strip is a skew shape where there's no two boxes in the same column. So here, this blue part here forms a horizontal strip. And analogously, a vertical strip is a skew shape where there's no two boxes in the same row. So here you can see a vertical strip. And this allows us to define the up and the dual down operator. So the up operator with an indexing variable x applied to some partition lambda is just a formal sum over all news, which are obtained by adding a horizontal strip to lambda. And each lambda is multiplied by x2 number of boxes we added to obtain new. And very similar, the dual down operator with index now y applied to some partition lambda is defined as the formal sum over all the partitions mu we now obtain by removing a vertical strip. And again, we have some variable y to the number of boxes we removed. And as homework until next FPSAC, you can think about like on which space these operators should live. Or if you don't want to wait until next year, you can just look at our paper. Okay. And using these operators, we can write the Schur polynomials in this way. So meaning we start with the empty partition, we apply n up operators, and then look at the coefficients of lambda. And the reason for this is that instead of thinking more like rows and columns, we think about like entries of the tableau. So first, if we start with the empty tableau, and then we add all the ones form a horizontal strip. So this is one thing here in this expansion of this formal sum. Then the twos, if you look only at the twos, again, they have a horizontal strip. So we see this shape here as one term in this expansion. And you can continue doing so. Okay. And similarly, we can write S lambda prime using these dual down operators. But now we apply these dual down operators to lambda, and then look at the coefficient of the empty partition in this expansion. Okay, so why are these operators really useful? So first of all, we have this commutation relation, which is, I would say, quite well known. And something which I feel is slightly less well known is that this commutation relation is actually equivalent to this Q version of the dual Cauchy identity. And this is not only true for Schur polynomials, this is whenever you have these up operators and dual down, or in the classical case, up and just down, they're equivalent to some Cauchy identity. And so the second part is actually quite easy to see. So the one side is these commutation relation is actually a special case of the Q version where we restrict to just one x variable and one y variable. And the other way around is you can obtain this by a very simple linear algebra argument. And for the rest of this first part, I want to focus a bit about this commutation relation and at least sketch a common control proof, which will lead us to dual local growth rules. And once you have these growth rules, it's very easy to see that you can use the framework of growth diagrams, or in our case, dual growth diagrams by Fomin, and you can transform a common control proof of this commutation relation to a common control proof of this dual Cauchy identity. Okay, so how do we do a common control proof of this commutation relation? So what we do is we fix two partitions, lambda and rho, and we apply both sides at rho, and we look at the coefficient of lambda. So if we do it on the first time, like we start with rho, we have to add all the cells which are in lambda but not in rho, and then delete at least all the cells which are in lambda but not in rho. And then we might add some extra cells and delete them as well, and this is encoded by this parameter k here. And similar for the other side, if we go first down, we might end up with some mu, and the mu has the maximum mu we can have. Yeah, the maximum mu we can have is the intersection of lambda and rho, but we might delete more cells, which is again denoted by this k. And then a common control proof just means finding families of bijections from this set to this set. And we can see this, so this set is just corresponding to this side here, and this set here. So this dk is if we take this 1 here in this expansion, and this dk minus 1 corresponds to this term xy, because we have to add and delete one cell less. And such a family of bijections we are calling a set of dual local growth rules. Okay. And so now let's look a bit more closer. And what we need are inner and outer corners. So inner corner generally is our cells we can remove, and we still have a partition. And outer corners are cells we can add, and it's still a partition. But in our case, we have some extra conditions with this lambda and rho. And so first, let me explain these pictures below. So we have intersection for lambda and rho for a specific sample. It's union. And here in the middle, I drew the union, where boxes which are in rho but not in lambda are green and have these vertical shading, and boxes which are in lambda and not in rho have these red horizontal shading. And so here are all the inner cells of the intersection, but not all. We are not allowed to remove all of them. So this condition we had beforehand basically says that we're only allowed to remove these cells with the minuses, which form together with the green parts, vertical strips, or which form with these red parts, horizontal strips. So this is also this reason for this shading. And all the mu's which satisfy this thing here, this condition, are corresponding to subsets of these removable, what we're calling removable inner corners. And similarly for the outer corners, we cannot add like all of them because we have this extra condition here. And the ones we are actually allowed to add are called addable ones. And these are those which form, again, vertical strips together with the green boxes, or horizontal strips together with these red boxes. Okay. And then, since we have this identification between the mu's subsets of the removable, the nu's subset of the addable ones, like the insertion rule means just mapping removable boxes to addable boxes. And there's two ways. We can do it either like in the column insertion way, where you map a removable one to the next removable in the next column, or in the row insertion way, where we map a removable one to the one in the next row. Okay. So this was about like classical RSK. So now what is changing if we go to the Macdonald setting? So first of all, we have as well up and down operators, now with some q and t parameters. And they show up in this function psi and phi star. And I'm not going to define these. In a sense, they've been defined in the lecture on Monday. But the important here is they don't look too bad. They're products of terms of the form 1 minus q something, t to the something, divided by 1 minus q to the something, and t to the something. And these somethings are basically hook and leg lengths of certain cells. And then, I mean, Macdonald polynomials were not defined by using semi-standard Young tableau, but Macdonald showed that we can express them using semi-standard Young tableau, or in our language here, meaning we can use up and dual down operators to define these Macdonald polynomials. And this is actually, it was a theorem for Macdonald, but it's our starting point. So we view this as the definition for Macdonald polynomials. And we aim to prove the properties of Macdonald polynomials starting from this definition in a combinatorial way. And so why are Macdonald polynomials important? Like one reason why they're important is they specialize to many very known polynomials. So we obtain sure polynomials for q equals t, the whole little was for q0, q Whittaker for t0, or the check polynomials if we set q to t to the alpha, where alpha is another variable, and then take the limit by setting t going to 1. Okay. So again, as before, we have these up and down operators, and this means like we have, on the one side, we have the dual Cauchy identity we want to prove, and we have this commutation relation. And what we aim for is a combinatorial proof of this commutation relation, because we then can use growth diagrams to obtain a combinatorial proof of this Cauchy identity, dual Cauchy identity. And as before, with this, for this combinatorial proof, we're looking at this mu's and nu's, meaning in this case, we can now not just do a bijection, because we have to prove as an identity like this. So on the left-hand side, this means like we first go down from rho to mu, we get this weight, and then from mu to lambda, we pick up this weight. And on the other side, we go from lambda up, from rho up to nu, we obtain this weight, or from nu down to lambda, obtain this weight. Or we could rewrite this a bit of like tinier, using this new notations, because we know that this mu corresponds to some subset of the removable cells of size k or k minus 1, and the nu's correspond to subsets of the supplementable or addable cells with of size k. And it's very easy to see, if you do this and look at examples, that if you want to find a weight-preserving bijection, it's not possible. The weights are so different, this cannot work. So we could stop here, but as for the talk in the very morning, we don't stop. We look at for some alternative, and the alternative in this case are probabilistic bijections. And so what is a probabilistic bijection? So assume you have two sets with some weight function. Then you can think of probabilistic bijection as kind of two probability distributions, P of mapping x to y, and the probability to map y back to x, which satisfy these three conditions. So first, if you fix an x, the probability that this x is mapped somewhere must be 1. If you fix the y, the probability that y is mapped back to x also has to be 1. And then we have this compatibility condition between the weights and the probabilities. And if you have all these three ingredients, then this shows that these two weighted sums are equal. And since math talks should have at least one proof, let's prove this very quickly. So we start here with this first sum. We use the first condition here to make the sum more complicated. We use this compatibility condition to change the weight and the probability to this second weight and this backwards probability. And finally, we can use this second property, and we have the sum we want. So if you find a probabilistic bijection, this shows those two weighted sets, the weighted generating function are equal. And you can think about this more in the sense of like, instead of proving that a bijection is surjective and injective, you're showing that a bijection is one by constructing its inverse bijection. So this is kind of the idea. 5 minutes? Okay. So let's construct these probabilities. And I now have to say I was slightly lying on my second slide. I'm not using French convention for like my whole talk, because if you've been to Montreal or Quebec in general, you know, like it's a French province. However, French people would say like people they are not talking French, they're actually talking Quebecois. So we shouldn't use French convention. We should what Gabe and I are calling Quebecois notation. So we're now drawing these diagrams in this way. And you see in a moment why this is way nicer in our setting. Okay, so first draw them. And then if you have like, assume lambda and rho are given, you calculated this removable, these addable cells. So these are now these pluses and these red minuses here. We define a bunch of points. For each addable or supplementable, so the S, you define points Si at the bottom right, or Si bar at the top left. And similarly for the removable, we are defining Ri at the bottom right, or Ri bar on the top left. And also for a reason which is clear in a moment, we're defining these kind of extra artificial points. So we're having I for inner corner, which is equal to Ri bar, or O for outer corner, which is equal to this Sj. And the reason we're doing this, defining all these points and now using Quebecois notation is that we are identifying points with coordinates x, y to monomials with q to the x, t to the y. And the important two things are that these boxes are all unit boxes, and what we are looking at are homogeneous rational functions of degree 0. So we don't care where the origin is. So everything is well defined. And then our definition for the forward probability is this very nice product. So remember, we have a set R of removable points, cells, which we have to map to a set S of addable points. And then the probability can be calculated by just using all these points. And the very nice thing is, for the backwards probability, which is denoted by P bar, what you're doing is you just add bars to all the S's and all the R's. And that's the formula. So it's like the forward probability and the backwards probability both have really small explicit formulas. And I'm having an example which I should skip probably for time reasons. So our main theorems is like first, these probabilities which I showed quickly form actually really a probabilistic bijection, which proves the commutation relation of this Q up, Qt up and Qt down operator. And using growth diagrams, we are able to obtain a combinatorial or tableau theoretic proof of the dual Cauchy identity for Macdonald polynomials. And I want to use, I guess I still have a few minutes left, for some properties. In particular, something we looked at is to specialize on the one side the input, like we would start with any 0-1 matrices on the one side, and on the other side specialize this Q and T. And for specializing the input, so first, if you specialize to matrices with at most one non-zero entry in each column, this corresponds like to words with letters 1 to n. Then what we obtain is really a Qt generalization of Robinson-Shenstedt correspondence for words. So like this is the common kind of playground between dual Cauchy identity and Cauchy identity. So we actually get a correspondence in this setting. And if you further specialize to permutation matrices, one is obtaining qRST, the Qt correspondence Gabe and I defined a few years back, which is generalizing just the classical Robinson-Shenstedt for permutations. And if you specialize Q and T, so the one property which makes really probability theorists very, very happy is if you take Q and T between 0, 1, or between 1 and infinity, like everything I call the probability is like really honest probability, so it stays between 0 and 1. And then for these other specializations, something really nice is this lemma here, which tells you what is happening if Q and T are inversed. And this can be seen very easily by this picture of this Quebecois notation. So if we're inverting Q and T, we obtain the very same probability as if you switch rho and lambda and conjugate every partition you see and switch q and t here. Okay. And now we can use this to do this kind of hierarchy of polynomials which are generalized by Macdonald polynomials. So starting with our Macdonald polynomials and our correspondence here, if you set t equals 0 or t to infinity, you obtain on the one hand like q-Whittaker polynomials, and our correspondence specialized to the row or column insertion for these polynomials, which was defined by Matveev and Petrov. Or on the other side, by setting q or to 0 infinity, we obtain a correspondence on whole little polynomials. And if you further specialize the other parameter, which is not specialized yet, you obtain the classical row and column insertions for RSK. But there's another very interesting point, which is obtained by doing the check polynomial limit. Because in this case, if we're restricting, if you're restricting to matrices with at most one non-zero entry per column, then what is called the P tableau. So in the usual RSK, you have two tableaus. The one is the recording and the insertion. So the insertion tableau, the P tableau distribution in this check limit is actually turns out to be invariant under interchanging two columns. And we proved this in our paper, and we've shown, it's not the case that we're not able to do this in the Macdonald case, it's just not true. So like this thing seems to be true in the check polynomial limit, but it's not true on a limit like somewhere on a level above. And we believe that if there's a qtRSK version existing, that this should exist, like this property should be satisfied there as well. Okay. Thank you very much.
So,
could you explain the example?
Yes. Okay, let's move maybe here. So here I just copied the formula of before. So in the example, lambda and rho are both 2, 1. So we have 2 removable cells and 3 addable ones. And then you have all these points here. And then, like here, what I wanted to calculate is the probability of mapping the second removable, like this minus here, to the 0th and 1st one. So meaning like adding this and this box. And then you just plug in the formula, you obtain this formula in these points. And then using, so in this case, it's very convenient to set this S0 point to the origin of our grid. And then you obtain this formula, and you can simplify it further to this. Yeah. So it's also actually, the formula is very useful to do actual calculation and to program it in the computer and so on. Yeah.
Do you think you can impose like algebraic or combinatorial conditions on the probabilistic bijection so that yours becomes the unique one?
Yeah, this is an open question. So it seems, so something I didn't tell, so, okay, maybe use this here. If we have, like with this compatibility condition, it shows that like a fraction of these probabilities always has to be something nice looking like this. And this was kind of our starting point, how to guess and come up with the definition for them, because we tried to write each probability with like the least number of these terms here. So in a sense, if you're familiar with algebraic Diophantine geometry, there's the concept of height function. And you could define the height of an expression like this by the maximum degree of like on the top or bottom. And then it seems like the probabilities we found are actually minimal with respect to this height. But of course, we have like so far no idea like how to prove it or yeah.
Just a technical question. So you just mentioned that the S naught is going to be the 0 point, right?
Sorry?
In terms of defining the coordinate, you just mentioned that the S naught is going to be the 0 point, right?
Yeah, so in this, it's just easier for this example to make this 0.
So it doesn't matter?
No, it doesn't matter because like this term here, it's maybe not, no, it should be obvious. Like here we have D minus size of R points. Oh no, yeah. If you go through this, it's maybe takes 1 or 2 minutes, and then it's obvious that this is a homogeneous rational function of degree 0. So it doesn't. If you can shift, like you can shift the origin, it doesn't matter.
Okay.
Okay. I'm not expert on this area, but as far as I know, there is a generalization of RSK for Cauchy identity of Whittaker functions.
For which functions?
Whittaker.
Yes.
Yeah, and due to not the different from the you mentioned on the last slide. Okay.
How does this?
You mentioned on the last slide. Yeah, but there is another version of RSK due to Imamura, Muchikoni, Sasamoto, you know?
So I know that there's, like now we're in the dual RSK setting. I know that for the RSK setting, there's generalization on the Q-Whittaker level, as well as on the whole little polynomial level. But I always forget like by how, like which author did like which, because they're, like sometimes it's like these two people, and then the second author is with somebody else, like proving this case and so on.
Yeah, I see. Thank you.
And we'll have one more question.
How does your bijection differ from RSK at Q equals T? At least from the example, it seems like they're different a priori.
Yes, so as you can see in this diagram, if you set T, like do the simple version, T0 and Q0, you get dual row insertion, or T infinity, Q infinity, you get column insertion. But then if you set like Q equals T, but don't specialize further, this means like you're in this check polynomial limit, and you're kind of stuck in between here. So this is the reason I didn't draw an arrow here. Like you've said Q equals T and then whatever, but not 0 and not 1, you get something, still probabilistic bijection, which is neither row and nor column insertion. So it's somewhere in the middle of in this space, yeah.
Right.
But it has for our, in the case when we do permutation matrices, we've shown that for, I think, the identity matrix, the distribution on the tableau or on the diagrams is related to the, now I forgot it. What is this? Is it Poisson? No. I forgot the word, like the name. It's for diagrams, which is, I think, connected to the longest increasing Plancherel, yes. So we get a Q Plancherel if we set Q equals to T. Thank you. Yeah.
So let's save the rest of the questions for the lunch break, and let's thank Florian again.